Hello, this is my lab 2 for Physics 1 at Tech, and in this lab we'll be exploring what happens when you drop an object and look at its acceleration due to gravity. So, we know that when an object is dropped, we assume that the only force that is going to be acting on it is the weight force. And the weight force is defined as negative m times g, where m is the mass in kilograms, and g is 9.8 meters per second, also known as the acceleration due to gravity. So, according to this formula, objects should fall at an acceleration of 9.8 meters per second squared towards the Earth. To illustrate this, I dropped a plus sushi from a standing position. So, we're going to look at this via Tracker. Alright, so in Tracker, here's the video of what happened. As you can see, I have the frames between frame number 9 and frame number 25 actually going on. So it's about 16 frames of data. So from the starting position, you see it's not moving, and I'm just holding it. And then as it falls directly along the axis, and maybe there's a little bit missing on it. You can see the calibration stick is set right about where it's about between right below the origin, and it's about 17 centimeters or so, which is the length of the sushi. And as it falls, it regressively goes faster, as you can see here in the chart. So if we actually pull the data from that and move it to Excel, in Excel we see that it actually falls along a pretty standard curve. Now, if we look at a computational model that I ran in Python, we see that the experimental model is significantly higher than what is expected from the computational model, which overpredicts how far it should have actually fallen. Which leads us to believe that the acceleration due to gravity may not be accurate because it seems to be accelerating slower than what's happening in the model. So this means that we probably have some other force than just gravity here. Knowing that the model is going to overpredict how far the object should have fallen, it means there's some other force that is pushing up on the object, preventing it from falling down at a straight 9.8 meters per second squared. So the other force acting on it has to be the drag force. The drag force is basically the force of like air resistance or other things that stops objects from falling at that sheer 9.8 meters per second squared. So for the drag force, we know that the formula for it is b times v, where v is the velocity at a given time, and b is some constant that is specific for each object. So since I don't know how to actually figure out what b is actually going to be, we can actually adjust the model using the drag force to adjust for the average acceleration that we found. Looking at the Python code, we see that the weight force is defined as the mass of the ball times the acceleration due to gravity times a vector to make it a vector force. Then we see that the drag force is going to be defined as the velocity of the ball, which is a vector, multiplied by b, which is defined here as 0.0217 to make it so it actually fits the experiment. And then it runs through the loop and gives us a there we go, a model that looks somewhat like this, where we see that the drag force is getting exponentially bigger as it goes further down. And it goes down continues on for about 6.64 seconds. Comparing a graph of what the model gives us to the experimental, we see that it fits at the beginning of the model and at the end of the model. However, it still overpredicts how far it should be in the middle of the model. This is probably due to some other forces that may take precedence, or it may also be due to the fact that I may have clicked the entire thing wrong. But either way, we see that the model is not perfect, or that the world isn't perfect, and that there are other forces contributing to the acceleration.